In this video, we're going to do yet another example of finding the limit of a function of two variables. We're given the function x y to the fourth over x squared plus y to the eighth, and being asked to find whether that limit exists or it does not exist as y approaches 0, 0. All right, so in this one, there's not a lot of algebraic simplification we can do. And it doesn't look like a lot of hope of trying to approach it any other way, so probably the limit doesn't exist. One of the good ways to check to see that the limit doesn't exist is I noticed that the degree of the denominator here would be an 8, while the degree of the numerator, if I add those exponents, would be a 5. And when your degree of the denominator becomes bigger than the degree of the numerator and you're approaching 0, 0, typically that limit's not going to exist. If I go under the premise that the limit doesn't exist, then I probably need to find a couple of different paths that we can approach the point that we're interested in and show that we get two different answers for limits. Well, one easy way to approach 0, 0 is to let either x or y be 0 and see what happens. In this case, I let x equal to 0. I plug in 0 everywhere I see x. On the numerator, I just get 0, because I get 0 times y to the fourth. The denominator is y to the eighth. My y value is still approaching 0. I simplify the 0 over y to the eighth to 0, and then that limit turns out to be 0. So if I go along the y-axis, go along x equal to 0, I get 0 for my limit. Now, if I try to choose the x-axis, let y equal to 0, I end up with the same thing. So that doesn't accomplish what I want to do, namely show that the limit does not exist. So I need to be able to pick a different path to try to show that the limit does not exist in this case. Well, one thing that could help me out to be able to do some canceling is if I were able to combine like terms in the denominator. One way that we could be able to combine like terms is if I see a y to the eighth where that x squared is. In order to see that, I need to replace the x with a y to the fourth. So when I simplify, I get y to the eighth. So I'll consider the path x equals y to the fourth. That still goes through the point 0, 0. If we replace x with y to the fourth, we get y to the eighth on top and a 2 y to the eighth on bottom. That accomplishes our goal for being able to do some canceling out. The y to the eighths cancel, we get 1/2. And if we take that limit as y goes to 0, we get 1/2. So now I've got two different answers for a limit, which means that the limit cannot exist. So let's see if we can look at a graph here again. Here is x equal to 0 going along the y-axis, and we notice that we really do stay at 0 the whole time, so that limit is 0. Versus if I go along the curve x equals y to the fourth, represented by this black curve here, I see that my z coordinate is always at 1. Excuse me, 1/2, not 1. So I get a limit of 1/2 in that case. And again, since we get two different answers for our limits when we choose different paths, we have to conclude that the limit overall does not exist.